All right, inverse functions. So an inverse function is a function that basically undoes a function. Um, it's kind of like the opposite function. And here's the steps to finding the inverse of f of x. Step 1. Verify f of x is 1 to 1. This actually isn't a super important step, because if it isn't, the function's just not going to be the inverse, or it just won't be a function. If it isn't a function, then we can still graph it, we can still do things with it. But if you can verify that your original function is a one-to-one function, the inverse will also be a function. Step 2. Simply replace the f of x in the notation with a y. You can go on to step 3. And in step 3, you switch every time you see an x, you make it a y, and every time you see a y, you make it an x. And you can go on to step 4, which is to solve for y. Step 4 might take you a little bit of time, and when you complete that and have y by itself on one side, you can replace y with the inverse symbol. And the inverse symbol is this, and it is pronounced f inverse. And that's the notation for inverse. Alright, let's take a look at an example walking through these 5 steps. So if we have an original function that's the square root function, if you want to graph this quickly, the square root function sketched looks something like this, and you can quite quickly tell that it is indeed 1 to 1, so that's good news. We know that our final solution will be a function as well. And let's start going through those steps. So y equals root x, then switch and make it x equals root y, and now solving for y. So the way to get rid of a square root is to square, so you square both sides, and I'll rewrite it as y equals, and then I replace with function notation and x squared. Now you'll notice that when I go and graph this one, the parabola that I get is it's a function, it's not a problem, but it's got a lot more information in it than the original green line. And what I mean by that is there's kind of 2 sides. There's one in this quadrant 1 and one in this quadrant 2. And what we didn't account for was some restrictions. So back here there was a restriction. X has to be bigger than or equal to 0, and that'll always make y bigger or equal to 0. And that means as I go down here, I'm going to get some restrictions. I'm going to get y is always bigger than or equal to 0, and x is always bigger than or equal to 0. And you notice I wrote those in the opposite order, and that's because of the inverse nature, we switch x's and y's. So I've switched x's and y's. In this case, it doesn't make much of a difference. But I don't want this half that's in quadrant 3. I just want this half, and I'll draw it in top in red, that's in quadrant 1. So this restriction still applies, or I guess is a new restriction that applies to our inverse function. One other nice thing about these functions is you can check to see if they're inverses. There's a rule for that. So let's write that down, and then we'll see if this one actually applies to that. It turns out functions are inverses only if f of g of x, I have an extra bracket in there, sorry, f of g of x, so g of x substituted into f of x has to equal x, and these both have to be true, g of f of x is always also equal to x. So I have f of x, and this is what we're going to be considering g of x here, the inverse. So if I substitute in my x squared, then normally f of x is equal to square root, but now it's x squared, and the square root of an x squared is an x. So that takes care of the first one. And g of, and instead of x, I'm now using f of x, which is root x. So g of x was x all being squared, but now it's root x all being squared, and you see that's also x. So if they undo each other and they turn out to just be the value of x, then you know that you have an inverse. So it's a way of double checking that this answer is correct, just by seeing if you can substitute g of x into f of x and get x, and f of x into g of x and get x. We can also do some graphing with inverses, so let's take a look at an example of that. So in this case, we want to graph f of x, and we'll define f of x as x squared plus 2, and we want to graph its inverse. And I'm just going to do a sketch for these. So here's my Cartesian plane, and I'm going to graph this parabola. So it normally goes through 0, 0, over 1, up 1, but the whole graph is up 2. So a little bit of practice of using some of the things that we talked about in the last day, over 1 and up 1, over 2, up 4, over 1, up 1 in the other direction, over 2, up 4 in the other direction, and play connect the dots. So that's what my graph looks like. I know some of these coordinates. I know that I have 0, 2, I know I have negative 1, 3, and I have 1, 3. I know I have 2, and it was up 4 plus 2 more, 6, and negative 2, 6. And I have a bunch of points. So, fairly well sketched out there. Now I need to go and actually calculate the inverse. So my original function is x squared plus 2. You can see that that original function isn't 1-to-1, so the final answer I'm going to get to this won't be a function, but that's okay. I can still graph its inverse. And so let's go and actually calculate what the inverse will be. So I make this y equals x squared plus 2. I switch the x's and the y's. I get the y's by themselves. And so I get x minus 2 on the other side, and I take the square root. And when I take a square root, I get a plus and I get a minus. And now going about graphing this, well, if we graph them one at a time, one of the graphs is the plus part. And so that looks like this. So that's a square root graph, and that square root graph has gone right 2. So if it normally goes through 0, 0, it's now right 2, and then 1, 1 from there, and 4 more and 2 from there, and it looks like this. There's your square root graph. And the other graph, I'll just do it in red, is negative of that square root graph. And so now I've got that function. This negative does a reflection, and it does a reflection over the x-axis. And so here's my x-axis, and the reflection will look like this. And you can see that that parabola that normally went up is now going sideways. And if you find some of these points, you have 2, 0, you've got 3, 1, down here you've got 3, negative 1, and you should be able to see a relationship between some of these points and their corresponding points on the other one, and that is that the x and the y's have been switched. 0, 2 is now 2, 0, 1, 3 is now 3, 1, negative 1, 3 is now 3, negative 1. So you can find this point, it corresponds, so it's 6, 2, not 2, 6. And this is a very fast way of being able to actually graph things without actually having to go through all the algebra and think about the transformation, the reflection, all those kinds of things. Another thing about these inverses is they are a type of reflection. They're a reflection over the line y equals x. So these points here, these points here, these points here, they're all exactly reflected over that diagonal line. Okay, let's take a look at what happens when we try to transform a point without knowing the function through the next example. So if we have a point like 2, 6, and we know that's on our original function, y equals f of x, what has to be a point that's on the inverse, but the inverse that's been translated? And so last time when we were talking about transformations, I said that order was important, and this is a point where order is definitely important. You need to do the xy switch first, the inverse switching the x's and the y's first before you apply any transformations. So in this case, there's a point 2, 6, and we know that that's on an original function and that we're dealing with an inverse. So do that step first. And I like to show it with these little mappings. I find that easiest. So when I take 2, 6 and I apply that inverse to it, when I do this to it, then it becomes 6, 2. The x's and the y's switch. Then I'm going to go and apply this transformation, and this transformation deals with the x's. It's with the x's, so it's actually the opposite. So it's left 2, not right 2. The x value is going to get smaller by 2. So to move it left 2, the x value gets smaller by 2, and I have my final answer. I think it helps if you stage it through with these little arrows. This is called a mapping, with these little mappings, to try to get the step-by-step notation. As we said last day, sometimes order matters, sometimes it doesn't. When it does matter, these step-by-steps are really helpful for the marker and for your own understanding of what you need to do first and second. When it doesn't matter, it's still helpful because you can make sure you actually took care of each change that needed to happen. And we'll see more of that in the future. All right, we'll see you in class.